There's a popular belief that humanity is nothing more than biological mold, confined to a tiny, rocky fragment orbiting an ordinary yellow dwarf star. That beyond our gravitational sandbox, there's no way out for us. We look up at the stars, see billions of them, and yet we understand that the chasm between us is not just vast. It seems insurmountable. Under videos about the future of space exploration, you often find fatalistic musings that any dreams of other worlds are just a way to escape reality. And in practice, the laws of physics have sealed our fate. And unlike flat Earth theories or moon landing deniers, skeptics of interstellar travel have a strong foundation. This isn't just whining, it's calculations. Scientists and engineers who have spent decades building spacecraft to explore our solar system understand all too well how hostile space is. When the conversation turns to flights to Alpha Centauri, the focus is usually on engines. Just give us antimatter or fusion, they say, and we'll fly. But let's be honest. Even if we had a magical gas pedal that could accelerate us to insane speeds, that would only be the beginning of a parade of problems, each capable of dooming the mission before it even leaves the Oort cloud. Today, we'll try to figure out if our situation is truly hopeless. Is the interstellar void as terrifying as it's made out to be? And why, despite all the obstacles, are we already, in essence, an interstellar civilization? We just haven't fully realized it yet. Welcome to the channel where we gaze into the abyss and try to understand how not to dissolve into it. Let's start with the classic skeptic's argument, microscopic death. Imagine a spacecraft hurtling at, say, 60,000 kilometers per second, about 20% the speed of light. At such speeds, space is no longer empty. What we call a vacuum is actually filled with rarefied gas and dust. Under normal conditions, we don't notice them. But at relativistic speeds, every hydrogen atom becomes a bullet, and every speck of dust becomes an anti-tank mine. Many people think the biggest danger in space is asteroids. But that's a misconception born of Hollywood movies. The asteroid belt is an incredibly empty place. If you stand on one asteroid, you probably won't even see the next one without a powerful telescope. Flying through it without hitting anything isn't luck, it's mathematical certainty. But interstellar dust is a different story. It's everywhere. When your ship collides with a particle just a few microns in size at a fraction of the speed of light, it's not just a mechanical impact. There's an instantaneous release of energy comparable to the detonation of explosives. The material at the point of contact turns into plasma. And if your spacecraft is a fragile structure of silicon and aluminum, after a few years of such travel, it will turn into a colander. But let's look at it from another angle. We already have objects that have left the influence of the solar wind. Our trusty Voyagers. Yes, their speed compared to relativistic speeds is like a tortoise's step. They'll need tens of thousands of years just to approach the influence zone of another star. But they're flying, and they're intact. Moreover, they've proven that we can build electronics capable of functioning in deep space for decades. Yes, their instruments are now being shut down one by one due to the degradation of radioisotope generators. But that's a battery problem, not the fact of being in space itself. The Voyagers are our message in a bottle. Even if humanity collectively decides to step aside tomorrow, these pieces of metal will continue their journey. They are physical proof that interstellar travel is possible as a physical fact. The question is only one of time and whether we want to see the results within the lifetimes of those who launched the spacecraft. Here we encounter what I call the technological curse or the dilemma of the starting time. Imagine, you build a massive generation ship. It's a colossal expense, decades of work. You launch it, and it flies to its destination for 300 years. Your grandchildren live on it, are born and die in the void. But 50 years after launch, a breakthrough in physics occurs on Earth. A ship is created that can cover the same distance in 50 years. We launch it, and it overtakes the first ship after just 10 years. As a result, those who flew on the first ship arrive at a destination already inhabited by the great-great-grandchildren of those who stayed on Earth. They arrive in an already established colony on an outdated vessel. The reasonable question arises. Was it worth launching the first ship at all? Wouldn't it be better to wait forever for the perfect technology? But if we only wait, we'll never begin. It's a vicious circle. Calculations show that there's a certain window of efficiency when the technology is mature enough not to be quickly overtaken, but early enough not to waste centuries waiting. Now, communication. This is perhaps the most underestimated problem. Suppose your probe reaches Proxima Centauri. It takes amazing pictures of an Earth-like planet. How do you send them home? Radio signals weaken proportionally to the square of the distance. At a distance of 4 light-years, an ordinary antenna becomes a useless piece of wire. For the signal to reach Earth and be distinguishable from cosmic noise, the transmitter on the probe must have monstrous power, or we need to build a receiving antenna the size of a small country on Earth itself. There's the option of laser communication. A focused beam of light scatters much less. But here we face the problem of aiming. You need to hit a receiver a few meters in diameter with a laser from a distance of 40 trillion kilometers. And don't forget that while the light travels those 4 years, Earth isn't standing still. It's racing around the sun, and the sun is racing around the center of the galaxy. You need to aim not where Earth is now, but where it will be in 4 years, accounting for all relativistic corrections. It's a mathematical hell. But even if we solve the aiming problem, there's the issue of energy. A tiny probe weighing a few grams, like in the Breakthrough Starshot project, simply can't carry a power source capable of piercing the void. The idea of using a chain of small probes as relays seems logical, but it complicates the mission 1,000-fold. Each probe in this chain must maintain its position perfectly. One failure, and the connection is lost forever. And yet, why do scientists continue to spend time on this? Why do people like Stephen Hawking or Yuri Milner invest millions in these concepts? Because we're at a unique point in history. For the first time, we see possible solutions. We're not just fantasizing about hyperjumps. We're calculating the power of lasers for light sails. Speaking of sails, this is perhaps the most realistic technology available today. We don't need to carry fuel with us. The fuel is light, either solar or, more efficiently, a powerful laser beam from Earth's or the Moon's orbit. A light sail is an incredibly thin film that catches photon impulses. Yes, the pressure of light is minuscule, but in a vacuum, with constant exposure, it allows for acceleration to insane speeds. The main problem here is how to make the sail strong enough not to be torn apart by the laser and light enough not to weigh tons. But suppose we solve the problems of protection, communication, and sails. We arrive at another system. And here we face a surprise that's often forgotten: speed. If we've accelerated to 20% the speed of light, we need some way to brake. Space isn't a highway where you can just hit the brakes. In a vacuum, there's no friction. If you don't have a reverse engine or a way to turn the sail to catch the light of the target star, you'll just zip through the Alpha Centauri system in a few hours. Imagine, you've flown for 20 years, spent billions of dollars, and you only have a few hours to photograph something at breakneck speed. It's like trying to make out details on a flying bullet from the roadside. To get quality data, we need to either learn how to brake using gravitational maneuvers or magnetic traps, or launch thousands of probes in the hope that at least one will fly close enough to a planet. And now we come to the most important question: why? Why do we need all this if the risk is enormous and the benefit unclear? The answer lies in the very nature of life. Life always seeks to occupy all available niches. We didn't leave the ocean for the land because it was easier, but because there was space. Interstellar expansion is the only way to ensure humanity against extinction in the event of a local catastrophe in the solar system. Many say we should first put our own house in order. But history shows that technological leaps during expansion have always helped solve problems at home. Water purification, solar panels, modern communication systems. All these are byproducts of the space race. Interstellar travel will force us to invent ways of producing energy and materials that will change life here on our small planet. Yes, perhaps we'll never build cities on Proxima as depicted in movies. Perhaps our first interstellar colonists will not be humans, but digital copies of our consciousness or autonomous builder robots. But that doesn't mean we're trapped. We're just at the design stage of the key to the door. The difficulties are real. Dust can destroy a ship. Communication can be lost. Funding can dry up. But the laws of physics don't say impossible. They say difficult. And difficult is exactly what humanity is best at turning into routine. 100 years ago, flying across the Atlantic was a deadly adventure. Today, it's a boring process where you sleep in a chair and complain about the food. Interstellar space is our next ocean. And while we currently only have flimsy rafts like the Voyagers, we're already learning to build caravels. We're ceasing to be inhabitants of a system and beginning to realize ourselves as part of the galaxy. And while the journey may take centuries, what matters is that we've already begun to move. We're not doomed. We're just at the beginning of a long journey home, to the stars. Let's continue our deep dive into the abyss. We left off with the idea that physics doesn't say no to us. It just presents a huge bill we can't yet pay. But for a moment, let's imagine that the issues of money and laser installations are resolved. We've built a ship. And here, the most fragile and capricious element of the entire structure enters the scene, the biological species known as Homo sapiens. If we decide to send living people to the stars, rather than a lifeless piece of silicon, the level of complexity skyrockets. And the first problem we face isn't food or oxygen, it's radiation. Within our solar system, we're protected by the sun's magnetic cocoon, the heliosphere. It deflects most high-energy particles flying in from the depths of the galaxy. But once we enter interstellar space, we're under direct fire from cosmic rays. These aren't just solar flares you can hide from behind a layer of lead. Galactic radiation consists of the nuclei of heavy elements accelerated to nearly the speed of light. They pierce through the ship's metal hull like a hot knife through butter. When such a particle hits a human cell, it doesn't just damage it, it literally shreds the DNA. On Earth, we're protected by a thick layer of atmosphere and a magnetic field, equivalent to a concrete wall several meters thick. Building a ship with such armor would make it too heavy for any engine to lift. Here, engineers begin to look toward unconventional solutions. For example, creating active protection, a powerful magnetic field around the ship that would deflect charged particles, mimicking Earth's magnetosphere. But this would require superconductors and energy levels that currently seem like fantasy. Another option is biological. Perhaps we'll have to genetically modify the colonists themselves, enhancing their DNA repair mechanisms so their bodies can recover faster than radiation destroys them. It sounds unsettling, but perhaps the interstellar human will differ physiologically from us as much as we differ from the fish that once crawled onto land. But suppose we protect the crew from radiation. Now comes the issue of time. Even at 10% the speed of light, the journey to the nearest system would take 40 years. That's an entire human lifetime in a confined space the size of a few football fields. And this isn't just about boredom. It's about the psychology of small groups. Imagine a crew of 50 people locked in a tin can for 40 years with no way out. Social friction, conflicts, depression. In such conditions, any minor issue could lead to catastrophe. How do we maintain social structure? How do we ensure that after 20 years of flight, the crew doesn't split into warring factions and destroy the ship from within? Psychologists at NASA and Roscosmos are already grappling with this, conducting isolation experiments like Mars 500 or Sirius. But a year in a ground-based module is a walk in the park compared to decades in the void, where outside the window there's always the same black abyss. This is why the idea of hibernation or suspended animation is so appealing. If we could turn off human metabolism for the duration of the flight, we'd solve a dozen problems at once. We wouldn't need as much food, water, or oxygen. We wouldn't need huge living spaces or exercise equipment to combat muscle atrophy. The crew would simply fall asleep near Earth and wake up at Alpha Centauri. But there's a catch. Nature didn't design humans for hibernation. We're not bears or ground squirrels. Our cells constantly require energy. If we simply freeze a person, Ice crystals would rupture cell membranes. Scientists are now studying xenon and other gases that could induce a state of deep torpor in the brain, but we're still infinitely far from being able to safely put a person to sleep for decades. And even if we achieve this, who will monitor the ship? Artificial intelligence. But is it ready to take responsibility for thousands of sleeping lives in the unpredictable environment of space? Speaking of artificial intelligence, there's a concept that removes biology from the equation entirely: digital colonization. Why send heavy bodies, tons of water, and food when you can send information? If we ever learn to fully scan human consciousness and transfer it to a digital medium, interstellar travel becomes a matter of data transmission. We simply transmit the code of a person to an automated station that has already arrived in another system and built infrastructure with the help of robots. There, your consciousness is loaded into a new synthetic body, and voila, you're on another planet, while the journey took only fractions of a second as your data traveled at the speed of light. Of course, this sounds like a cyberpunk plot, but if we're talking about the scale of the universe, biology is a very inefficient way to travel. We're too fragile, too short-lived, and too dependent on a narrow range of temperatures and pressures. Space belongs to machines, or to those who can become part of the machine. But let's return to more grounded matters, if we can call them that. Nutrition. On a generation ship, or even a fast research vessel, there must be a closed biosphere. We can't take 40 years' worth of food supplies with us. We'll have to grow it right there. And this isn't just a vegetable patch. It's a complex ecosystem where human waste becomes fertilizer for plants. Plants produce oxygen and absorb carbon dioxide, and bacteria process everything else. The problem is that we still haven't been able to create a perfectly stable closed ecosystem even on Earth. The Biosphere 2 project in the 1990s ended in failure. Oxygen levels dropped, insects died out, and people began to starve and quarrel. In space, we won't have the option to open a window and let in fresh air. Any imbalance in the bacterial population could cause the crew to suffocate or be poisoned by their own metabolic waste. This brings us to a philosophical question. Is the very idea of conquering the stars a flaw in our thinking? We're used to thinking in terms of colonization, arriving, seizing, reshaping to suit ourselves. But space doesn't want to be reshaped. Perhaps, instead of building huge ships that imitate Earth, we should learn to live in space itself. The development of orbital stations, mining resources on asteroids, and building cities inside hollow celestial bodies is an intermediate step that will prepare us for the leap. If people learn to live in artificial worlds within our system for generations, then for them, a flight to another star won't be a stress. It will just be a long move from one home to another. For a space human who has never seen the sky or felt the wind, the interstellar void won't be terrifying. It will be a natural habitat. But there's another barrier that's rarely discussed in popular science programs: the barrier of social expediency. Imagine a modern government allocating $1 trillion to a project whose results will only be seen in 80 years. Politicians live by electoral cycles of 4 to 6 years. They need to report to voters here and now. An interstellar mission is a project that requires societal stability over centuries. Will we be able to maintain unity of purpose if, during that time, regimes change on Earth, wars are fought, or economic crises occur? Who will maintain contact with a probe that has been flying for 50 years if the generation that launched it no longer cares, and the new generation is more interested in solving problems like global warming or resource shortages on our home planet? Interstellar travel requires us to become something greater than just a collection of competing states. It requires us to become a unified species with a planning horizon spanning centuries. This is why private space exploration and enthusiasts like Elon Musk or Jeff Bezos are so important. They're trying to take space out from under the dictatorship of short political cycles. But even their ambitions are currently limited to Mars. The stars are a game of an entirely different level. Let's touch on another technological niche: gravity. In a long flight, the absence of weight kills humans. Bones become brittle, Vision deteriorates due to fluid redistribution in the head, and the heart weakens. To fly for decades, we need artificial gravity. The simplest way is rotation. The ship must be a giant rotating donut or dumbbell. But this creates enormous stresses on the structure. Combining rotating living modules with huge engines and fuel tanks so that everything doesn't fall apart during acceleration is an engineering nightmare. What if we take a different approach? What if we don't accelerate to insane speeds? There's a theory of slow spread. Imagine we simply begin to colonize the outskirts of the solar system. First the Moon, then Mars, then the moons of Jupiter and Saturn. Then we move on to Kuiper Belt objects. We build stations on icy dwarfs billions of kilometers from the Sun. For the inhabitants of these stations, the boundary between our system and alien blurs. They already live in eternal darkness, using nuclear energy. For them, jumping to a neighboring icy object halfway to another star is routine. We can colonize the galaxy like lichen spreading over a rock, slowly, centimeter by centimeter, adapting to the conditions. In this scenario, we don't need photon drives. We just need to learn to live in the void. It will take not decades, but millions of years, but on the scale of the universe, that's just a moment. And here we encounter the Fermi Paradox. If this path of colonization is so logical and physically possible, albeit difficult, where is everyone else? Why don't we see traces of such lichen on the outskirts of our system? Why haven't automatic probes launched millions of years ago by civilizations older than ours arrived? Perhaps the answer is that the interstellar barrier is the great filter. Maybe civilizations either die before leaving their system, or they change so much in the process of adapting to space that we simply don't recognize them. Or, more likely, they realize that interstellar travel is a huge risk with minimal return. Why fly to a real star when you can create a perfect virtual reality inside your supercomputer and live in it forever, consuming the energy of your sun? But we are human. We are curious. We are driven by the same itch that drove ancient Polynesians into the open ocean in fragile canoes. They didn't know if there was land out there. They only saw birds and believed in the stars. Interstellar travel for us isn't just a technical challenge. It's an act of faith that we matter, that our presence in the universe shouldn't be limited to a single point. Yes, the skeptics are right. At our current level of development, we can't fly to the stars. We can't protect ourselves from dust, we don't know how to brake at relativistic speeds, and we don't know how to keep our sanity in the void. But look at the progress. Just 400 years ago, we had only just learned that the Earth wasn't the center of the universe. 70 years ago, we first put a simple radio transmitter into orbit. Today, our robots drill rocks on Mars and photograph oceans on Jupiter's moons. Interstellar travel isn't a stupid idea. It's the ultimate goal that pushes us to jump above our heads. Even if we never reach Proxima Centauri in human form, the very process of preparing for this leap will make us stronger, smarter, and perhaps wiser. We'll stop being just inhabitants of Earth. We'll become those who dared to challenge infinity. So, the next time you see a comment under a video saying, "We're not going anywhere," remember, that's what they've always said. They said humans couldn't survive the speed of a train. They said heavier than air machines wouldn't fly. They said space was the limit. But here we are. We're looking up. And as long as we look up, we have a chance. The stars haven't gotten closer, but we've gotten better at seeing them. And one day, perhaps, the light from one of our lasers will catch up to that very Voyager, pass it, and continue on to other worlds, carrying the code of our civilization. This will be our first real step into infinity. And while it will be difficult, easy paths have never led to great discoveries. We continue to scale up. We figured out how hard it is to keep life alive inside a ship, but let's return to the hardware and the very fabric of space. If we acknowledge that the biological body is too heavy a burden, an entirely different engineering universe opens up before us. And here, a concept that sounds like science fiction but is actually based on rigorous calculations comes to the fore, using the gravitational lens of our own sun. Imagine we don't need to fly to Alpha Centauri to see its planets as clearly as we see the moon. According to Einstein's general theory of relativity, mass bends spacetime. The Sun is a giant lens. If we send a telescope to a distance of about 550 astronomical units from us, 4 times farther than Voyager 1 is now, we'll reach a point where the Sun's gravity focuses light from distant star systems. At this point, our star acts as a colossal eyepiece. With a relatively small mirror, we could obtain an image of an exoplanet with a resolution of a few kilometers. We'd see continents, oceans, forests, and perhaps even city lights, if they exist. This would be a virtual interstellar journey. But to deliver a telescope there in a reasonable time, say, 10 years instead of 100, we'd still need those acceleration technologies we've been talking about. And here we again run into the issue of energy. Let's talk about what could realistically replace chemical rockets in the next 50 years. Ion engines are already operating on our satellites, but their thrust is negligible, comparable to the weight of a sheet of paper. To accelerate a heavy ship, we need a nuclear electric rocket engine. This is when a small nuclear reactor on board generates electricity that accelerates plasma to enormous speeds. This isn't fantasy. Prototypes of such systems are being developed in several countries right now. Such an engine won't allow us to travel to the stars at the speed of light, but it will make all our interplanetary space accessible and fast. This will create an industry that will serve as the foundation for the real leap to the stars. But there's another exotic option often discussed in niche circles, using magnetic sails. Instead of catching laser light, we could deploy a giant loop of superconductor that creates a magnetic field. The interstellar medium is plasma, and the ship's magnetic field would repel it. It's like a ship sailing under a sail using ocean currents. The most interesting part is that a magnetic sail is ideal for braking. When you approach the target star at high speed, you activate the magnetic field, and it begins to rub against the plasma of the alien star's stellar wind, effectively slowing you down without expending fuel. This leads us to the idea that the ideal interstellar ship isn't a single technology, but a hybrid. Laser acceleration near Earth, magnetic braking at the destination, and a nuclear reactor to sustain life and communication along the way. Now, let's look even further to where the physics of solid bodies ends and the physics of extreme states begins. If we ever learn to manipulate antimatter on an industrial scale, we'll have the most efficient energy source in the universe. The annihilation of a gram of antimatter releases as much energy as the explosion of 20 kilotons of TNT. An antimatter engine could accelerate a ship to 50 to 70% the speed of light. The problem is that currently, we can only produce antimatter atom by atom in accelerators like CERN. The cost of 1 gram of antimatter is measured in quadrillions of dollars. But remember, aluminum was once more expensive than gold, and it was used to make cutlery for emperors. Today, we throw away aluminum cans. Technologies always scale. If we find a way to capture antimatter in space, where it exists, trapped in the magnetic fields of gas giants, or produce it efficiently in orbital factories near the sun, the speed barrier will fall. But even with infinite energy, one question remains. Will we become a galactic empire? Probably not. And the reason lies in the theory of relativity itself. Information cannot travel faster than light. This means that any interstellar colony will be completely autonomous. You won't be able to call Earth and ask for advice in real time. The answer will arrive in 10 years. Interstellar humanity won't be a single state. It will be a scattering of civilizations separated by time and space. Each star system will develop in its own way, acquiring its own culture, language, and perhaps even biological traits. We'll turn into thousands of different species, united only by a common past on a distant, half-forgotten planet called Earth. And perhaps this is the true purpose of evolution, to scatter the seeds of life so far that no catastrophe in the universe can destroy them all at once. Yes, today we look at the stars with pessimism. We see vast distances, deadly radiation, and a lack of resources. But imagine what a primitive human felt, looking at the raging ocean. For them, it was an insurmountable wall of water, the end of the world. They couldn't know that beyond that horizon lay other continents. They just built a raft. We're currently at the same raft-building stage. Our satellites are the first chips thrown into the surf. Our calculations are attempts to understand the direction of the wind. Interstellar travel isn't a dream of a stroll in an alien park. It's hard, dirty, and dangerous work to expand the boundaries of reality. And those who say it's impossible simply forget what humans are made of. We're the product of 4 billion years of survival in conditions that constantly tried to kill us. We've survived ice ages, supervolcano eruptions, and asteroid impacts. We've learned to fly, split the atom, and edit our own genetic code. Do you really think a few light years of void will stop us forever? The void isn't a wall. It's just a place where nothing exists yet. And it's our calling to fill that void with meaning, technology, and life. We may not see the first photo from the surface of a planet in the Alpha Centauri system tomorrow. Our children or grandchildren may do it. What matters is that we're already asking the questions. We're already designing lasers. We're already arguing about how to protect a chip from cosmic dust. This means the process has begun. And once the human mind latches onto something, it doesn't let go until the problem is solved. The stars aren't just points in the sky. They're our future. And no matter how complex the problems of communication, energy, or biology may seem, they pale in comparison to one simple truth. We don't want to stay here forever. We're wanderers by our very nature. And our journey is just beginning. Space is vast, but our potential is even greater. We will fly, not because it's easy, but because it's the only way to remain human. Beings who always strive beyond the horizon. See you in infinity. This is Andrew from the channel Cosmos Simply. Look up. It's much more interesting than it seems beneath your feet.